Star-Y connection, definition, configuration, and symbolic representation. A star, also called Y, connection joins the three ends of three identical impedances at a common point called the neutral. Think of three roads that meet at a roundabout. The roundabout is the neutral and each road leads to a different corner of a triangle. The three outer ends are attached to the three supply lines, commonly called phases A, B, and C. The schematic symbol looks like the letter Y: three lines radiating from a central dot. If the neutral is brought out, the system can provide both line-to-line, a -B, B-C, C-A, and line-to-neutral, a -N, B-N, C-N voltages. In power distribution, a star connection is often used because the neutral gives a convenient return path and allows the use of lower voltage, single-phase loads, for example household lighting. Delta connection, definition, configuration, and symbolic representation. In a delta connection, each impedance is linked end-to-end, forming a closed loop that resembles the Greek letter delta, a triangle. No neutral point exists inside the loop. Every corner of the triangle is directly connected to a line conductor. Imagine three people holding hands in a circle. Each person represents an impedance, and the circle as a whole is the delta. The schematic symbol is a triangle with each side labeled with the impedance Z delta. All three line conductors are attached to the three nodes of the triangle. Because there is no neutral, only line-to-line voltages are available. Delta is common in motor windings and high-power industrial equipment because it can handle higher line currents without needing a neutral and provides a higher phase voltage than a star connection for the same line voltage. Line-to-phase voltage and current relationships in star and delta with numerical examples. Star line voltage V sub L is the voltage between any two lines. It is square root of 3 times the phase voltage V sub PH. V sub L equals square root of 3 times V sub PH. Star line current I sub L equals the phase current I sub PH. I sub L equals I sub PH. Delta line voltage equals the phase voltage. V sub L equals V sub PH. Delta line current is square root of 3 times the phase current. I sub L equals square root of 3 times I sub PH. Numerical example. Assume a three-phase supply of 400 volts line to line. Star phase voltage equals 400 volts divided by square root of 3, approximately 231 volts. If a balanced load draws 10 amps per phase, line current equals 10 amps. Delta phase voltage equals 400 volts, same as line voltage. If each delta connected impedance draws 10 amps phase current, line current equals square root of 3 times 10 amps, approximately 17.3 amps. These relationships help engineers size conductors and select protective devices. Current example with power. Suppose each phase of a star-connected load consumes 2 kilowatts real power at 0.8 power factor. Phase apparent power S sub PH equals P divided by PF equals 2 kilowatts divided by 0.8 equals 2.5 kilovolt amperes. Phase current I sub PH equals S sub PH divided by V sub PH equals 2.5 kilovolt amperes divided by 231 volts, approximately 10.8 amps. Line current equals 10.8 amps. For a delta version delivering the same 2 kilowatts per phase, V sub PH equals 400 volts. S sub PH equals 2.5 kilovolt amperes. I sub PH equals 2.5 kilovolt amperes divided by 400 volts equals 6.25 amps, and line current equals square root of 3 times 6.25 amps, approximately 10.8 amps, the same line current as the star case, confirming the power equivalence. Power calculations for balanced star and delta loads, including three-phase apparent, real, and reactive power. For a balanced three-phase system, total apparent power S3 phi is star S3 phi equals 3 V sub PH I sub PH equals square root of 3 V sub L I sub L. Delta, the same formula applies because V sub PH equals V sub L and I sub PH equals I sub L divided by square root of 3. Thus, S3 phi equals square root of 3 V sub L I sub L for both configurations. Real active power P equals S times power factor. Reactive power Q equals S times sine phi, where cosine phi equals power factor. Example, a balanced load draws 5 amperes per phase at 230 volts star with power factor 0.9 lagging. Phase apparent power. S sub pH equals V sub pH I sub pH equals 230 volts times 5 amperes equals 1.15 kilovolt ampere. Total apparent power. S3 phi equals 3 times 1.15 kilovolt ampere equals 3.45 kilovolt ampere or square root of 3 V sub L I sub L. Line voltage approximately 400 volts. Line current 5 amperes. Square root of 3 times 400 times 5 approximately 3.46 kilovolt ampere. Real power. P equals S3 phi times power factor equals 3.45 kilovolt ampere times 0.9 equals 3.105 kilowatt. Reactive power. Q equals square root of S squared minus P squared equals square root of 3.45 squared minus 3.105 squared approximately 1.5 kilovolt ampere reactive. The same numbers are obtained for a delta load delivering the same phase power, because the overall three-phase power expression is identical. Key takeaway: for balanced loads, the total three-phase apparent power depends only on line voltage, line current, and square root of 3, regardless of star or delta wiring. Derivation. Consider one phase of a balanced set of impedances. In star, each impedance is ZY connected from a line to neutral. In delta, each impedance is Z delta between two lines. By looking at the two-port network between any two lines, the impedance seen looking into the delta is the series combination of two Z delta in parallel with the third Z delta. For a balanced case, the relationship simplifies to Z delta equals 3ZY. ZY equals Z delta divided by 3. This result can be derived by equating the line-to-line impedance of the two configurations. Sample problem. A three-phase motor is rated at 10 ohms per phase when wired in star. What is the equivalent delta impedance per phase? Using Z delta equals 3ZY, Z delta equals 3 times 10 ohms equals 30 ohms. If the motor is wired to delta, each winding now sees 30 ohms, producing the same line-to-line voltage drop and thus the same power. Reverse conversion example. A delta-connected balanced load has a phase impedance of 48 ohms. Find the star equivalent. ZY equals Z delta divided by 3 equals 48 ohms, divided by 3 equals 16 ohms. The star version draws 1/3 the phase current for the same line voltage, which is why many large motors start in star, lower current, and run in delta, higher torque. Balanced system, all three-phase voltages have equal magnitude and are displaced by 120 degrees. Currents in each phase are equal. In this ideal case, star and delta behave predictably using the √3 relationships described earlier. Power calculations are simple because the neutral current in a star is 0, the three-phase currents cancel. Unbalanced system, one or more phases have different magnitudes or phase angles, often due to a fault, a single phase load, or unequal impedances. Effects. Star connection. The neutral carries the vector sum of the three-phase currents. I sub n equals I sub a plus I sub b plus I sub c if the neutral is solidly grounded. It provides a path for the imbalance, protecting equipment. However, unbalanced voltages can cause voltage sag on the weaker phases. Delta connection. No neutral exists, so the imbalance appears as circulating currents within the delta loop. These circulating currents do not flow to the supply, but cause extra heating in the windings and can distort the line currents. Analysis. Use symmetrical component theory, positive, negative, zero-sequence components to quantify the impact. The zero-sequence component only flows in star with a grounded neutral, delta blocks it. Therefore, delta is preferred for systems where grounding of zero-sequence currents is undesirable, for example to limit earth fault currents. In practice, designers may choose star for distribution networks to provide a neutral for single-phase loads, and delta for motor banks to avoid neutral current and reduce circulating currents. Conceptual question: explain why a large three-phase induction motor is often started in star, and then switched to delta. In star, the phase voltage is reduced to VL divided by square root of 3. So the starting current, which is roughly 6 to 8 times the full load current, becomes about 1/3 of the delta starting current. This reduces stress on the supply and the motor's windings. After the motor reaches about 70 to 80% of rated speed, the torque is sufficient to switch to delta, restoring full line voltage for normal torque and power. Numerical question: a 30 kilowatt, 415 volt line to line 3-phase motor has a rated full load current of 45 amperes. Star phase voltage equals VL divided by square root of 3 equals 415, divided by 1.732, approximately 240 volts. Starting current in star is approximately full load current multiplied by the ratio of phase voltage to line voltage, i.e. 45 amperes times 240, divided by 415, which gives about 26 amperes. Because line current equals phase current in a star connection, the line starting current is about 26 amperes, roughly 58% of the delta starting current, which would be about 78 amperes. Switching circuit question: draw and label a simple star-delta starter circuit using 3 contactors K1 star, K2 delta, K3 main, and a timer. Operation sequence: when the start button is pressed, K3 main and K1 star close, energizing the motor in star. After a preset timer, for example 5 seconds, the timer coil releases K1, opening the star contactor, and simultaneously K2 delta closes, placing the motor in delta. Explanation: comparison of advantages, disadvantages, and application criteria for star versus delta configurations. Exam-focused summary. Voltage per phase: V sub pH equals V sub L divided by square root of 3 lower. V sub pH equals V sub L full line voltage. Current per phase: I sub pH equals I sub L, same as line. I sub pH equals I sub L divided by square root of 3, line current higher. Neutral available: yes, enables single-phase loads, provides a return path for unbalanced currents. No, neutral absent, only line-to-line connections. Starting current: induction motor, approximately 1/3 of delta starting current, useful for soft start. High, about 6 to 8 times full load current. Power handling: better for distribution, low voltage lighting, and when a neutral is needed. Better for high torque, high power equipment, motors, generators. Harmonic content: zero sequence currents flow to neutral can help filter some harmonics. Zero sequence currents trapped may increase circulating currents and heating. Typical applications: power utility feeders, residential commercial lighting, small motors, transformer secondary, large industrial motors, generators, welding transformers, high power drives. Design trade-offs: requires a neutral conductor, extra cost. Star-connected loads see reduced voltage, which may limit torque. Exam tip: remember the square root of 3 relationships. Star, V sub L equals square root of 3 times V sub pH, I sub L equals I sub pH. Delta, V sub L equals V sub pH, I sub L equals square root of 3 times I sub pH. Also, star gives a neutral, delta does not. Bottom line for exams: if a question mentions a neutral, low line to neutral voltage, or starting a motor with reduced voltage, think star. If it mentions high torque, no neutral, or the same voltage on all 3 lines, think delta. Use the conversion formulas: Z delta equals 3ZY and V sub L equals square root of 3 V sub pH for star, or V sub L equals V sub pH for delta, to quickly check calculations.